In this video, I'm going to describe how to find the orthogonal complement of a subspace of Rn. And in order to do that, we should understand what I'm talking about, what an orthogonal complement is. So to give ourselves some perspective, V is a subspace of Rn, so a subset that's closed under addition, scalar multiplication, and contains zero. And the orthogonal complement of V is going to be everything in Rn that is orthogonal to everything in V. I'm missing a line here. It's all of the vectors in Rn such that when I take that vector and dot it with anything in V, I get 0. Let's look at an example. So we're working in R3, and our vector space is going to be this green plane through the origin. And I'm not going to tell you what the space is, what the equation defining it is. That doesn't matter for right now. I want to know what vectors are orthogonal to everything in this space. And I'm going to give you an example of one such vector. So this purple vector here is orthogonal to everything in the green subspace. And just to show you what I mean, here's one vector in the green subspace. This red vector, you can see if you kind of look at the correct angle, that this is orthogonal or perpendicular to the purple vector, and it's in the subspace. And then similarly, if I draw a different vector, this blue one, this is in the subspace. We got to look at a different angle. The purple and the blue vector are perpendicular, so they're orthogonal. Their dot product is 0. And we can go take a step further because it's R3 and we can visualize it. We can kind of see what's going on, that this, in some sense, this vector is just perpendicular to the plane. And so every vector in that plane will be orthogonal to every vector, or sorry, to this vector, this purple vector. And it's not hard to really see that we can take this a step further. Anything that's perpendicular to everything in the green plane has to just be a multiple of this vector. And so I can draw a picture. What is our orthogonal complement? It's this orange line. Right? Any vector that lies on this orange line is going to be perpendicular or orthogonal to everything in the space, including the 0 vector, right? The 0 vector is orthogonal to everything because when we take the dot product with anything, we get 0. So this is one example of what I'm talking about, what an orthogonal complement is. I'm going to give you a second example. What if I started with the orange line? So the orange line is a subspace of R3. And if I wanted to know what is everything that's orthogonal to the vectors on this orange line, for instance, this is one vector on the orange line, well, this blue vector is something that's orthogonal to everything on the orange line. Similarly, this red vector is something that's orthogonal to everything on the orange line. And you can maybe see where I'm going. That green plane that we were looking at initially consists of all of the vectors that are orthogonal to everything on the orange line. So I want to take what we've just talked about, this R3 visualization, and say a few more things about the orthogonal complement. Okay, so first of all, I guess when I refer to this, instead of saying the orthogonal complement all the time, we often read this as V perp. Right? This symbol here is the perpendicular symbol. And as we've discussed, orthogonality is kind of a generalization of things being perpendicular. And so V perp is the way that we say the orthogonal complement of V. And we write it like this, V with a superscript perpendicular sign. What have we learned so far? Well, I don't know if I explicitly said this, but so some properties. In this example, we saw that V perp was another subspace of Rn. So V is a subspace of Rn just by definition. That's what we're starting with. V perp is also a subspace of Rn. What else did we notice? Well, one thing that we noticed is that when I started with so vperp, in our example, initially v was the green plane and vperp was that orange line. And when I asked, well, what is the orthogonal complement of vperp, I got my original space back. Another way of saying this that I think is a little maybe less confusing is that if W is the orthogonal complement to V, then V is the orthogonal complement to W. There's this symmetry here. And so this is definitely going to be a useful property. Some things that I noticed but I didn't explicitly say. You can think about the R3 situation and convince yourself that if your original space is two-dimensional, your orthogonal complement is going to be one-dimensional. And if your original space is one-dimensional, then your orthogonal complement is going to be two-dimensional. And there aren't that many options in R3 because 3 is small, but generally speaking, the dimension of your original space and of your orthogonal complement always add up to the total dimension of the space. So dimension of V plus dimension of vperp is n, the total size of the space. And there's one final property that I'm not really going to dive into, but I just want to write it down now because we'll use it later. And we'll really use it kind of in the background. It'll be really important for a lot of the facts that we use, but we won't directly use it all that much. And that's that if you take any vector in Rn, you can write it uniquely as a vector in V plus a vector in vperp. So if we start with any vector x in Rn, we can write it in exactly one way. As a sum v plus w with v in v and w in vperp. Again, a fact that I'm not going to write an example of this because I don't know how instructive it is. You can look at the picture and try to convince yourself of it. It's going to become important. The fact that we have this uniqueness allows us to do some really slick calculations when we start to apply this stuff, for instance, to linear regression. Okay, so let's get into the calculational side of things. So I've presented what vperp is, right? It's the orthogonal complement. It's defined like this. How do we figure out what it is? And we'll start with our R3 example. In R3, you can kind of just figure it out visually, but what we'll do will translate nicely to other dimensions. Okay, so let's look at the process. How do we find vperp? And by finding vperp, I mean, how do we figure out a basis for vperp? So here's our process. We'll start with a spanning set, or maybe a basis of V. A basis is always a spanning set, right? A spanning set might have extra vectors that are redundant, but it doesn't matter. Either way, if we have a full spanning set of V, we're going to create a matrix whose rows are the vectors of the spanning set, and then vperp will be the null space of that matrix, and we know how to find null spaces. So let's go back to our example. So in our example, I'm just going to draw two vectors, the two vectors we were working with before. These vectors are a spanning set, right? It's a two-dimensional space. They aren't multiples of each other. And so in this example, spanning set, there's lots of choices here for what the spanning set is, but the one that I've drawn, the red vector is that's not right, 3 minus 2, 4, and the blue vector is minus 6, 1, minus 1. So what am I going to do? I have a spanning set. That was step one. And I'm going to move away from the picture here so that I have space to write. I'm going to put these as the rows of a matrix A. And I'm going to find the null space of this matrix. And remember, finding the null space of a matrix is the same as solving the corresponding homogeneous system. I think I wrote this wrong, right? I had a minus here. And so I need to solve the system given here. So what am I going to get for a solution? You can try to do this on your own and then follow what I do. This is a simple one, so I didn't work it out ahead of time. So let's just see what we get. I can right away get rid of that -6 by adding to row 1 to row 2. And so that'll give me a 0 here. Not a 5. A -3. And a 7. And to solve this homogeneous system, let's get rid of the 3 and the -3. So let's multiply our rows. I'm kind of rushing through this, but if you're unclear on these steps, I recommend revisiting the videos on solving linear systems, right? Because it's still very relevant to what we're doing. So here I went through and got rid of those coefficients by multiplying each row by a constant, and then finally I should get rid of the -2/3 here to get to reduced row echelon form. And to do that, I had to add 2/3 of this row up, so -14/9 plus 12/9 is -2/3. And so I get this. And now I have to go and solve this. Or sorry, now I have to translate this into the actual solution. So I've gotten as far as I can with matrices, right? Now converting this into solutions, we have a free variable. So x3 is s. And then I have x2 is 7/3 s. And x1 is 2/3 s. And if that's unclear at all right, I just paused the recording. I finished saying if that's unclear at all, and this should be unclear. I realized that I had made a mistake. So I apologize for that. Yeah, when I added this up, this was supposed to be a -2/9. This is why I should work stuff out ahead of time, especially when I'm making a video. I realized that my answers didn't line up with what I was expecting because they were wrong, which will happen. Okay, and so what this gives us is that our solution set is x1, x2, x3 equals s times 2/9, 7/3, 1. And so this vector here, the set containing just that vector, is a basis for the null space. Or in other words, V perp is the span of 2/9, 7/3, 1. Let's put this to the test. I'm going to go into Desmos, and you can't see what I'm typing, but I'm going to take this vector here, and I'm going to change it to 2/9, 7/3, 1. And I'm going to really hope that I'm right. And it did. It worked. All right, so this vector spans the whole space. The whole space is that orange line. So back to this process, just to revisit, we had a spanning set, and if we didn't know a spanning set, we would have to find one, right? There are various ways to do that. But once we have a spanning set for the space we're trying to find the orthogonal complement of, we place it as the rows of a matrix. We reduce that, we solve the linear system, the homogeneous system corresponding to that matrix by reducing to reduced row echelon form. Once we get our solution, that gives us a basis for the null space. In this case, it's one-dimensional. Vperp is the span of that space. I want to do another example where we go up to R4, because I like working with these lower dimensional examples because they allow you to see that your answers are right, and they allow you to verify that your visual intuition lines up with what you get from calculations. But they also can be overly simplistic. So let's look at an example in R4 to see how this works out when we can't visualize anything. And I'm just going to start with a space defined by its span. So V is going to be the space that's spanned by the following three vectors. 2, 1, minus 3, 4. 1, minus 2, 7, 0. 5, 0, 1, 8. And so I want to find Vperp. So I'll put these vectors as the rows of a matrix. And for this example, I am not going to walk through the process of solving the corresponding homogeneous system. I'll let you do that on your own if you want. So remember, when we're solving corresponding homogeneous systems, the zeros don't get changed. And so one way to think of this is I just need to look at the reduced row echelon form of A, and that'll tell me what the solutions to that system are. The zeros in the right never change with row operations. And so the reduced row echelon form that I get, and you can do this using software, by hand, whatever you like. I recommend any chance to practice and confirm that you can get the same answers is always a good opportunity, especially if you're having any issues with this. Is this. So this is the reduced row echelon form of our matrix A. And so that means that the solutions to our corresponding homogeneous system our free variables are x3 and x4. And so if I call x4, let's do them in order. I guess I'll call x3s and x4t. Then what do I end up getting? I end up getting that x1 is negative 1/5 s minus 8/5 t. And x2 is positive, not negative, 17/5 s minus 4/5 t. And when I split this into pieces, again, if you're unclear on these steps, go back to the video of Gauss-Jordan elimination, where I'm working with solution sets and writing solution sets as vectors as to how I get these answers. When I split this up, what I get is the s component is minus 1/5, 17/5, 1, 0, and the t component is minus 8/5, minus 4/5, 0, 1. And so Vperp is the span of these two vectors. We can't look at this visually because it's in R4, but we got an answer. I want to observe something. It's always useful to be thinking about what you think your answers are going to be and seeing whether your answers line up with what you think they're going to be. Maybe I should have said this before posing the question. If I look at this, what do I think vperp is going to look like? Well, we're in R4. I have the span of 3 vectors. I was kind of thinking vperp was going to be a one-dimensional subspace because I just told you that the dimensions add up to the total dimension. But we didn't get that. We got that vperp was a 2-dimensional subspace. This isn't a contradiction. Notice that looking at this reduced row echelon form, V is the row space of this matrix. And when we did this reduced row echelon form, we got a row of zeros. This is saying that the row space actually has dimension 2. This spanning set is redundant. This is actually a 2-dimensional space. This vector is 2 times the first plus the second. So even though we might have thought we were going to get a one-dimensional subspace, we can see through our work, okay, wait a second. The original space wasn't 3-dimensional. We had a spanning set that wasn't a basis. It had a redundant vector. So we started with actually a 2-dimensional subspace, and its orthogonal complement will also be 2-dimensional. And that's what we got here. Okay, I'm done with examples. I just wanted to quickly do the kind of why it works section of all of this. And I think it's best just looking at an example of why it works. What we're doing here is we're solving AX equals 0. Right? That's the whole process. We're figuring out the null space, which is the set of things that are AX equals 0. And remember, this 0 is a 0 vector. It's a 3-dimensional 0 vector. And so in order for AX to equal 0, if you work this all out, how do we get this first entry? We take X and we take the dot product with the first row. And to get this second entry, we take X and we take the dot product with the second row. And then to get the third entry, we take X and we take the dot product with the third row. And so in order for AX to equal 0, we need that when we take the dot product of X with any of the rows, we get 0. But that's exactly what we're trying to do, right? We're trying to find all of the vectors that are orthogonal to everything in the span, which is the same as saying that it's orthogonal to everything in the spanning set. So actually this setup is very intuitive in some sense, right? I just presented it as a method, but if you had started trying to figure out how should I solve this, this would be a very natural way to set up. It's not some totally magical thing. So it's a nice process, right? It involves things we already know how to do. And just kind of one more time, once we have a spanning set or basis, we take that, we put it as the rows of a matrix, and now we're back to something we know how to do. We find the null space of that matrix, we get a basis for that null space, that basis is also a basis for vperp.